Hello, guys. Welcome to Ramta Solutions and welcome to your grade 12 work and power past paper series. Today, the past paper that we are looking at is from the Limpopo province. It was written in September 2018. Okay, it was written in September 2018. I love this question paper for two questions of it, 5.1 and 5.2. Maybe I should have said I love this question for two reasons. Question 5.1 and question. The reason why I love question 5.1 is because in most of the past papers, they define the work energy theorem. And, getting something different excites me, right? Getting something different excites me. And now, okay, let's not waste any time. Let's get into the questions. So remember, guys, we have 12 minutes to complete this question. If we say we are slow, we must have taken 15 minutes. But of course, because I've already taken 1 minute of our time, we must finish at 13. Let's say 13:30. Cool. Now, the diagram below illustrates a child of mass 20 kilograms sliding down a frictionless. Hear the word frictionless. I want you to highlight it. It's very important that you highlight frictionless. Okay, it's important. A frictionless ramp. Okay, a frictionless ramp. Okay, it's very important that you highlight that. So now define a non-conservative force. Okay, we're not going to waste time. 5.1, what is a non-conservative force? It is a force for which the net work done in moving an object between 2 points depends on the path taken. Otherwise, you can also say it's force for which its net work is non-zero or it's not zero. Okay, but I will take the former. Okay, so now I will say non-conservative force is force for which the work done in moving an object between 2 points between 2 points depends on the path taken. Depends on the path taken. Okay? Depends on the taken. Or if you like, you can say it's a force for which its net work done is not equal to zero. But it's okay. I prefer this one for you guys. Okay? 5.2 says, let's go back. 5.2 says, use the relationship work done by a non-conservative force is equal to change in potential energy plus change in kinetic energy to show that in the absence of non-conservative forces, mechanical energy is conserved. So we're saying work done by a non-conservative force is equal to change in potential energy plus change in kinetic energy. So in the absence of non-conservative forces, this basically says, you are going to mechanical energy. Remember, the law of conservation of mechanical energy applies when there is no non-conservative force. Okay, so now it says, basically this question wants you to prove the law of conservation of mechanical energy. Okay, so because they say in the absence of non-conservative forces, this means this part will be zero because there is no conservative force. And what is this? Let's just expand this. It'll be mgh final minus mgh initial plus half mv final squared minus half mv initial squared. Okay, so let me take these guys with the negative to the other side. So it'll be mgh initial plus mg plus half mv initial squared. Do you see that? I took them to the other side. Equals mgh final plus half mv final squared, right? What is this? We know that the sum of the object's potential and kinetic energy is mechanical energy. So let's call it Emech initial equals Emech final. Remember, guys, we said mechanical energy is the sum of the object's sum of the object's potential and kinetic energy. So this part here is what we refer to as mechanical energy. But this is mechanical energy initially, and this is mechanical energy finally. Okay? All right. So, therefore, we should conclude, I believe. So they say, use the relationship to prove that in the absence of non-conservative forces, mechanical energy is conserved. Therefore, in absence of non-conservative forces, in the absence of non-conservative, in the absence of non-conservative forces, mechanical energy is conserved. Can you guys see that? Remember, to say mechanical energy is conserved is to say that mechanical energy initially is equal to mechanical energy finally. Mechanical energy is conserved. All right? And we have proven that. Can you see that? We have proven that. Now, let's go to 5.3. It says, use the principle of conservation of mechanical energy to calculate the speed of the child on landing at the bottom at point B. Okay, they say the coefficient, it's a new question. So this question ends here. All right, so we're going to use we're going to use the law of conservation of mechanical energy. We just proved, we said mechanical energy so we're gonna say EP at point, EP at point A plus EP plus kinetic energy at point A is equal to EP at point B plus kinetic energy at point B. Okay, it's simple. This is basically this. So let's do it. So I'm gonna say mgh at point B plus half mv B squared equals mgh at point A plus half mv A squared. So let's look at point B. Point B, what is our height? It's 0. Can you guys see that? Our height is 0. Okay, so this is, what is the mass of the baby? The baby was 20 kilograms. Okay, the baby was 20 kilograms. Okay. So this is 20 kilograms times 9.8 times 0. Even if you write 0, it's okay. Half times 20 kilograms. We do not know what this is. Remember, we are looking for the speed of the child at point B. Okay, perfect. Equals 20 times 9.8 times the height. Was it 5 point? The height is 5.1 meters. So there we go, 5.1 meters. 5.1 meters plus half. What is the mass? It's 20. What is the initial velocity? We need to be careful. Okay, we need to be careful. So they say that what we are basically assuming here, because they say this child is sliding down in frictionless. Okay, they didn't directly tell us that the initial velocity, they didn't they didn't give us the initial velocity here, but with the information given, we will take it to be 0, because it's here at this point. We will take it to be 0 since there is no other force playing a role here. We will take it to be 0. Okay, we'll take it to be 0. So initial velocity, or velocity at point A, will be 0. Okay, So this is 0 plus 10 VB squared equals, let's see, 20 times 9.8 times 5.1 is 999.6. 999.6 plus 0. So VB squared equals 999.6 divided by 10. Come on, it's easy. This is 99.96, isn't it? 99.96. Therefore, what is VB? VB is the square root of this guy. What is the square root of 99.96? It is 9.997. So basically, let's call it 10 meters per second. Okay, I'm gonna call it 10 meters per second because we get 10,00. So let's just call it 10 meters per second. Okay, so the speed of the child at point B is 10 meters per second. Now, the coefficient of kinetic friction between the child and the horizontal surface at the bottom of the ramp is 0.2. Interesting. If the child stops, I want you to highlight the word stops. Okay, I want you to highlight stops, right? You're highlighting stops. When they say stop, it means final velocity or velocity is 0. Okay, so if the child stops at C, use energy principles to calculate the distance x that the child travels before stopping. Okay, so here, 5.4, preferably, let's use work energy theorem. Okay, preferably, let's use work energy theorem. And the reason is simply, it's only friction here that we are interested in, okay? Because there is no force that the child applied to move himself forward, right? So the only force that will be doing work is friction. Now we know what is friction. What we know friction is coefficient of. It's the coefficient of kinetic energy multiplied by normal force. What is that? Normal force, we know it. In this case, it will be mass times gravitational acceleration. All right? It will be mass times gravitational acceleration. So let's substitute this. It will be, what is friction? It will be coefficient of kinetic friction multiplied by mass times gravity. Be careful. Delta x cos theta equals half mv, I think it's c squared minus half mvp squared, isn't it? Perfect. So let me take this guy, let me highlight him out. Okay, so we know what is the coefficient of kinetic friction. Let's go back. It was 0.2, right? It was 0.2. Okay, it was 0.2, so we are cool. 0.2, so this will be 0.2. The child weighed 20 kilograms. Gravitational acceleration is 9.8, and the distance, it is what we are looking for. But this distance, they didn't call it delta x. They called it x, and I believe this is capital X. So I'm gonna write capital X. Okay, I'm gonna write capital X. Now, friction always opposes motion. It will be 180 degrees. Cool. Now, at point C, the child stopped, right? And we found the velocity of this child at point B, which was 10, isn't it? Which was 10. Happy? So this is 0.2 times 20 times 9.8. What is this? It is, cos 180 is negative 1. So this is negative 39.2x equals 0 minus, what is this? 10 times 100. I believe it's a 1,000, isn't it? it's 1,000. So minus 1,000. Okay. So x is 1,000 divided by 39.2. What is it? It is 25.51 meters. Okay. It is 25.51 meters. Okay. All right. So this is it, guys. This is how you attempted this question. Okay. This is how you attempted this question, or how you're supposed to attempt it. Okay. Now remember, guys, if you want to get in touch with us, you can contact us. Check us out on our website, www.ramtasolutions.co.za. And from the same website, you can get blog posts that has different topics on physics, different topics on mathematics. Alternatively, you can follow us on your favorite social media platforms. And you can also talk to us on WhatsApp. On our website, you can get a link that will direct you to our WhatsApp contact, and you can converse with us. So, with that being said, ours ends here, and we thank you for your time with us, and all the best with your studies, and bye-bye.